Alright, welcome back to the differential equation series. So in the last video, we went over the basics of what the Laplace transform is, which is this ugly but beautiful equation. We went over how it turns a differential equation into an algebraic equation, where it's a function, just like a number. Like say you have f of x equals x squared. Well, you plug in a number here, say it's 2, and then it'll spit out a number. In this case, is 4. Well, the Laplace transform is another function, but inside this function, well, what you do is you don't feed it numbers. You feed it actual functions. It's like a cannibal. It eats other functions. And in return, it spits out another function in terms of a different variable, s. So, in the last video, we went over the Laplace transform of 1, and it equals 1 over s. Now, we're going to see what happens if we feed in another function e to the at into here. We'll go through the integration and all that, and we'll see what it spits out. Then we'll probably go over the Laplace transform table that you will have on your exams by just convention. I don't think many classes expect you to memorize or go through this whole process for every single question. There may be one exam question where you need to go over like the basic one or like one of these just once to prove that you know the application of how it, like, where this all comes from. But for the most part, we go over the integration just to give a basis, like a foundation, but then we're going to just be using a table that helps us go from the t world to the s world, and then we're going to do inverse Laplace transforms, where it's pretty interesting. You use a Laplace transform of a function t to get it in the form of s, and then you find the inverse Laplace transform to get it back into the form of t. And when you do that, you will get this Nuba equivalent function that is your solution to the differential equation. But one more thing before we start. I'm going to be moving into college for my 3rd semester. I'll have other classes to be diligent with and working as a tutor and maybe research. So I'm not going to say I'm ditching this YouTube channel, but I'm probably gonna maybe upload like 1 video a week or like none until like break or the summer. But maybe I'll finish this Laplace unit because that's the end of differential equations. Anyways, getting distracted, let's jump right into this. So the function we're going over this time is f of t equals e to the at. And we want to find the Laplace transform of that. Last time we found that the Laplace transform of 1 just equals 1 over s. And well, we're going to get a more elegant solution for this complicated thing. Eat is what it is. But anyways, let's jump right into it. So the Laplace transform of e to the at equals the indefinite integral of e to the minus st, and then f of t is e to the at dt. So first, this is ugly. So I want to simplify this a little with some algebra. And, well, with some basic like basis and exponent rules, we can combine this to be negative s plus a times t in the exponent, and we just have the same base. And this is an indefinite integral. They're delicate. We have to be like careful with them. So we can't just plug in infinity, but we can plug in the limit as some number goes to infinity. So we'll say c, and we'll find the limit of this integral from 0 to c as c approaches infinity. And this is with respect to dt. So let's jump right into it. So I'm looking at this, and we can actually integrate this already. So we have the limit of c approaches infinity of, well, this integral is just going to be e to the negative s plus a times t over negative s plus a. And we can verify this by taking the derivative. You have this stays the same, but you multiply by the chain rule, and it cancels out. We get what we had earlier. It's just a basic integral from like calculus 2. But so we plug that in. We get e to the minus s plus a times t all over negative s plus a. And this is evaluated from 0 to c when c approaches infinity. So, one thing I want to point out is this is a constant. So we can pull this out, and let me create some room here. We don't need this. So we can pull this out as just 1 over negative s plus a. And then we still have this limit as c approaches infinity of e to the minus s plus a all times t in the exponent of the limit of the bounds from 0 to c. And, well, this equals 1 minus s plus a times, well, if we plug in c for t, we get, well, there's two different cases. If we have a negative s plus a, if that is greater than 0, well, we have a exponent to a base to a positive exponent, and then you plug infinity times that, it's just going to go to infinity. So this would result in a solution that does not exist. It diverges. But if we have negative s plus a is less than 0, then we have this in the denominator. It would be the same as just e to the s plus a. As this approaches infinity in the exponent, well, it gets 0, closer and closer to 0, so it will converge. So we do get a solution. Happy face. So this would result in, well, we get our constant, 1 over negative s plus a, times, well, 0. We plug in infinity here. We're going to assume that negative s plus a is less than 0. And then, well, we plug in 0 for t, and we just get e to the 0, which equals 1. So minus 1. So we end up getting, if you follow me over to the left, we get 1 over negative s plus a times negative 1, which is the same thing as just 1 over s minus a. So the Laplace transform, the algebraic form of e to the at in terms of this new variable s, just equals 1 over s minus a. It's going to become more and more clear as we do more examples, and you're probably still looking at this like, what does this mean? How does this help? We're going to do some examples, but in order to do examples, you need to know how to do Laplace transforms and inverse Laplace transforms. So just bear with me as we journey our way through this, and it will make sense soon enough.